So in this video I want to show you how to use Excel to analyze and process your LDH experimental data. You may have downloaded a spreadsheet that looks like this from Blackboard, and it looks quite complex at first glance. And so what I want to do is I want to distill this into a simpler spreadsheet, looking just at a patient serum and also normal serum. And I'll show you how to turn this data, how to graph it, how to analyze it, how to process it. And along the way I'll show you how the calculations work, how the calculations tie into the Excel formulas, and also along the way I'll also show you a few tips and tricks on how to use Excel to the best of its abilities. So let's go and have a look at the raw data that you would have measured from the spectrophotometer in this experiment. In this particular worksheet, what you see is 3 replicate samples of patient serum measured using 5, 10, and also 20 microliters of the patient serum. And on the same sheet, right next to this, we've got a normal serum, which has 2 replicate measurements, one done using 100 microliters of serum and one done using 150 microliters of serum. What you'll see here is that down the side on this column, we've got time listed in minutes. Now this is important because later on, if we flick back to the spreadsheet I prepared earlier, you'll see that the slope and also the other calculations that we'll need have the time quantity, listed in minutes. And so if you have your time listed in seconds, it's a good idea now to convert them into minutes. So 0.25 minutes is just 15 seconds. So if we go back to our raw data, what you can see is that we've actually typed down the serum volume numerically. So we haven't put 5 ULs over here, 5 microliters, we've just put the number 5 in the cell. And this is important because this way we can actually get Excel to grab the number 5 from this particular cell, for example B3, later on when we come to use calculations. The other thing you've noticed here is we've used a micro symbol as opposed to just using the letter U. Now using the letter U is okay, and you can just type UL to represent microliters, but a special trick that you can learn is to actually type micro using a special keyboard trick. Now this keyboard trick is known as an alt code, and as an example, here's a quick animation from Wikipedia showing an alt code. So you notice that ALT is pressed first and held down, while on the number pad the user types 161. So again, on the number pad 161 while the ALT key is held down. Now the way to work this for the micro symbol is to hold down the ALT key and type 0181. So I'm holding down the ALT key here and I'm going to hit 0181 on my number pad, and lo and behold the micro symbol appears up here. Now some other things that you can start getting used to in Excel are things like formatting column widths and also merging cells. So you see that over here, our time in minutes, it's kind of cut off. And so what we can do is we can put our cursor right between the A and the B, and you see how the cursor changes from the kind of plus from the arrow to this two-sided arrow. What we need to do now is we can either click and drag this left to right, and we can see that that'll expand that column, or we can just double click it and it'll snap to the necessary width. The other thing that is nice to do in Excel is to merge and center cells. And so for example here we've got cells C1 and also D1, they're actually blank, even though they refer to the 10 and the 20 microliter samples for the patient serum. So what we can do is we can actually merge these 3 cells together and also merge these 3 cells together to make things a bit neat. So what we'll do is we'll highlight these 3 cells and we'll come up here and click the merge and center button. What it'll do is it'll merge those 3 cells, make them become one cell, and it'll center the text in that cell as well. So if we just repeat that for the other ones, serum volume for example for the patient BCD, select that, come up here, click merge and center, and we'll do the same for the normal and also for the serum volume for the normal too. Just makes things a bit neater. Now the first step in analyzing our numerical data is actually to draw quick graphs and have a look at how the data actually is represented. And so what we'll do is we'll insert an XY scatter graph. Now in science, remember, always insert, always draw XY scatter graphs, do not draw line graphs. Okay, so the XY scatter graph we want to draw is just one that has simple dots, and the way that I most prefer to insert an XY scatter is actually not to select values and let Excel guess at what I'm trying to plot, but I prefer just clicking in a blank area of the sheet and then going to scatter, selecting on the first option. And what this will do is it'll tell Excel to insert a completely blank graph. Now the benefit of getting Excel to insert a completely blank graph is that you can tell Excel exactly what you want to plot. And so if you right click onto the graph area, what you can see is there's a select data option. Now when you click on the select data option, it'll bring up a new box asking you to insert the data sources. Okay? And what we want to do is we want to create two graphs, one for the patient serum and one for the normal serum. The graph for our patient serum will have three sets of colored dots. Okay, one set will represent the values for the 5 microliter serum, another set will represent the absorbance values for the 10 microliter serum, and the next set will represent the absorbance values for the 20 microliter serum. Okay, so what we need to do now is we need to add these data series, and we do so by clicking the Add button. So when you click on the Add button, you add a new series. And now you can see that Excel asks you for a series name. So because we're going to draw the 5 microliter series first, what we can do is we can type in 5 microliters of serum using our keyboard. And the X values, what we could do is, remember the X values have to be the independent variable and the Y values are the dependent variable. So over here, the independent variable is the time. And so what we'll do is we'll click into this X value cell. We'll come over here to the time, and we just want to select the numbers, okay, not the title of the column, just the numbers. And over here in the Y values, what we want to do is we want to delete or backspace the existing value, and the Y values have to be the absorbance values now. So we go over here and we select the absorbance values. So it's click and drag, release the mouse, and then what you see is Excel has plotted this with the time on the X-axis, the absorbance on the Y-axis, and we've finished entering the data for our series. So what we'll do is we'll click OK now, and then we'll continue adding the data for our next two series, which are for the 10 and for the 20 microliter serum volumes. So to do that again, it's just add. We can type in 10 on our keyboard and micro. Remember using the alt code 0181 liters of serum. X values again is just the time, and the Y values, if we kill that off, equals the absorbances. Okay, and I'll just add the 20 microliters now. Okay, so once we've added our three series, what we can do is we can click OK to get out of this particular screen. So for our graph, it's nice to have a few titles that describe what the graph is trying to say. And so what we can do is we can add a title above the chart, and we can also give the axes, both the Y and the X axes, titles to describe what they're actually showing. So in order to add the axis titles, we come over here to Chart Tools, okay, and we click on the Layout tab. If you can't see the Layout tab of Chart Tools, make sure you've actually clicked into your graph, and then come to Layout tab, go to Axis Titles, and then let's add a horizontal axis title. We click on that button, and what we can do now is we can type in using our keyboard. This is the time, and the units are in minutes. Now remember, always put units down next to any measurement as long as the measurement actually has units. Okay, so we have our X-axis labeled now. Let's label our Y-axis. What we can do is let's go over here and we can select a rotated title. Okay, so the rotated title here, what we have on the Y-axis is the absorbance, so let's just type in A340 because it's the absorbance at 340 nanometers, and we'll just enter that using our keyboard. And finally, let's add a graph title. Okay, so we come here to Chart Title, and let's have a title above the graph, and we can call this the patient serum. Okay, and the other thing that we don't really like is seeing these unnecessary horizontal grid bars, and so in order to get rid of them, all you need to do is click on the grid bars using your mouse, and you can see how they've been highlighted, and you just press delete on the keyboard to get rid of them. Okay, so now that we have the graph for our patient serum, we can create a graph for our normal serum. A quick way to do that is just to right click on the graph itself and copy and paste the graph. And so what we'll do is we'll select the copy option, and then we'll click somewhere else in the worksheet, and then on our keyboards we'll press Ctrl V. Alternatively, you can come up here and press the paste button. So what this will do, this will make a copy of the graph, and what we'll do now is, using this copy of the graph, we'll actually adjust what data it is actually showing. So our normal serum only has two series that we need, one for 100 microliters and one for 150. So what we can do is we can come up here and select the green series, because we no longer need 3 series, we just need 2 series. We choose the green series, and notice how all the points are selected, and we just have to hit delete on the keyboard and it'll kill that series off from our graph. The next step is to change the data that the two existing series plot. And to do that, what we do is, again, we left click on one of the series, okay, and you notice again how all the series dots are actually selected. And you notice over here as well that the series values are highlighted in blue. What we can do is we can actually put our cursor over the edge of this, and you notice how our cursor changes from a fat plus to a skinny plus with an arrow. And what this means is that Excel is now allowing us to change or to move this box around. So what we can do is we can click and drag this, and this can become our 100 microliters. Okay? And we can do the same for our red series. So again, you can click on the corner, on the edges rather, and drag it over to the 150. And obviously this means that we need to now change the labels, and to do that what we do is we right click on somewhere in our chart, right click, and we choose the select data option. Okay, this will bring up the familiar dialog box again, where we have our two series, the blue and the red, representing our 100 and also 150. So we just need to come in, select one of these series, click the edit button, and now actually input a name for it. Okay, so this one is the 100 microliters of serum. Click OK. And the second one is actually our 150 microliters of serum. Click OK, and then OK again, and we've done. And so all we need to do now is obviously just to change this title to normal serum. Okay, so let's put these graphs side by side so we can actually analyze what they're talking about. So what we can see here is an increase in absorbance over time in both our normal and also our patient serum. The important thing to note with this particular graph is that even though it looks like the rate of production or rate of change of absorbance is linear, it's actually not that linear, or not as linear as you think it is. So a quick way to show or prove that to ourselves is to go up here into the Insert tab, select the Shapes option, okay, and just draw a straight line onto the curve. The benefit of doing this is that instead of getting Excel to try to force a trend line onto these samples, we can draw a straight line ourselves and actually think about it in terms of, are these lines actually straight? Okay, so when we come and click and drag a new line manually, what we can see, so I'll click this and I'll drag it along here, what we can actually see is that the absorbance is not increasing linearly over time. Okay, and if I draw two other lines just to satisfy our curiosity, I'll draw one of these lines for the red series, and I'll draw another line for the blue series. So what these manually drawn lines tell us is essentially that the absorbance does not increase at a linear rate throughout the entire time of our reaction. The linearity of this reaction only really occurs between about 25 or 0.25 minutes in all the way to about 1.5 minutes. Okay, so what you can see, for example, which is quite prominent in the 20 microliter serum series, what you can see is that the linearity really does start to drop off after about 1.5 to 1.75 minutes. It's less obvious in the 5 microliter serum because the substrate isn't quite running out, but definitely is at the 20. So what this means for us is that when we come to calculate the rate of change of absorbance over time, we can't actually take into consideration the entire 2 minutes of the reaction. So let's zoom in and have a look at what this means. Okay, so, oops, a bit too far. Alright, here we go. Okay, so if we have a look at our 20 microliter sample, we can see that the rate of increase is linear between about 0.25 minutes all the way up to about 1.5 minutes. And so the rise will only be here, and the run will be here, which means that the gradient will be calculated between the data points of 0.25 and also the 1.5 minutes. For our red, a similar example exists. So here is our red. We have our run like this, and this is our gradient. And for the blue, again, it looks like it's linear from here to there. Okay, it starts to taper off around there, and it starts to taper off even more around there. And so therefore we can really only take this as our run, and therefore this is our rise. Okay, let's zoom out. So functionally, what this means in Excel for us is that when we try to calculate the gradient of this line, also known as the slope of the line, we can't actually take into consideration our entire data set. Okay? Even though it's nice to have our data set here to prove to ourselves that it does actually taper off over time, we can't use the entire data set when we come to calculate our slope. Okay, so in order to calculate slope, let's drag these two graphs further down. Give us a bit more space. Let's delete these manually drawn lines. Okay, so what we've talked about before is how the slope of the line, the gradient, okay, is the rate of change of absorbance over time. Okay, so y over x is the rate. What we need to do now is we essentially need to get Excel to work out for us what this slope is between this 0.25 mark in time and the 1.5 mark. And so a really important function that would be good for you guys to know is essentially the slope function in Excel. So let's get Excel to work the slope function out for us. Alright, so we'll put the slope for these data points in here. Okay, we'll put the slope for these data points in here. We'll put the slope for these data points in here, and so on. So let's start a new row. Let's make this equal to slope. Remember, always put units in, and the units here will be absorbance over time, because it will just be the y, which is the absorbance, over the time, which is the minutes. And so it will actually be the change in absorbance over time, and a way to write change in science is to write the capital Greek letter delta. Okay, so what we'll do is we'll type slope, start the bracket up to indicate that we're starting the units, and come over here to our insert symbols. Okay, so insert tab, go to the symbol button, and what we can do is we can insert the Greek capital letter delta. If you can't see delta here, what you can do is over here you can select different types of characters and just select the Greek and Coptic. What you can do is it'll bring up a selection, okay, of Greek and also Coptic letters, and what you can do is find the delta. Where is the delta? There it is. Okay, so once you click on the delta, you can click insert, okay, and you see that it's actually inserted that character for us. Then we can click close. So the slope is the change, or the delta, okay, absorbance. We can type 340, and it's per minute. Enter. And again, let's resize our columns to make this a bit prettier for us. And what we can do again is just to come put our cursor between A and B, and we can double click on it, and Excel will snap this to size. The next step is to get Excel to work out the slope for us. We can do this quite simply using a particular function in Excel called the slope function. Now, whenever you get Excel to do a mathematical calculation for you, you need to start by the character equals. Okay, so for example, if we want Excel to work out the sum of 2 plus 1, what we can do is we can do equals. We can select the 2 using our mouse, and then we can press plus on our keyboard, and we can select 1 using our mouse again. Okay, and then we press enter, and the result is shown there as 3. Now this is very simple. What we can do instead is we can get Excel to use these special things called functions. Okay, so what we just inserted was a formula, equals something plus something else. We can also insert a function which is equals a particular word, okay, and then that word will instruct Excel to do a mathematical calculation for you based on a set of data. So the particular function that we're going to use now is the slope function. Okay, so in order to insert the slope function, we again type equals. Okay, and the slope function is very literally SLOPE. So we'll type SLOPE, and you can see that Excel has kind of shown us that this slope function is available for us to use. So right now you can either double click on this little option here, or you can just very simply start the brackets off. So it's just a parentheses, a left parentheses, and what you can see Excel has done is it's changed the hint, okay, and it's showing us that it wants us to feed it the known y values first, followed by a comma, and then the known x values. Okay, so because we want rise over run, we want the absorbance over time, our y values are absorbance, our x values are time. And remember that we want to only plot, or we want to only consider the absorbance values between time 0.25 and 1.5 minutes. Okay, so what we'll do is we'll select the absorbance values at these time points, okay, all the way from 0.25 minutes to 1.5 minutes. So these are the absorbance values of y values. We'll type in a comma now, and then we'll select the x values. Okay, so close the brackets, and we press enter on our keyboard, and what Excel has done is it's calculated this slope, or the gradient of the line between the time points 0.25 okay, and 1.5 using these data points. Now another powerful function of Excel is this thing called click and drag. Okay, so what you can do in Excel is actually, in order to save you time in having to type out this formula again and again for this cell, this cell, this cell, and this cell, what you can tell Excel to do is actually to propagate this formula across the entire row of cells. And so in order to do that, what we can do is we can put our cursor or point our cursor over the bottom right side of the cell, and you notice how it changes from this fat plus to a skinny plus, and we can literally click our mouse and drag this across the screen. But before I release the mouse, this actually won't work very nicely, and you'll soon see why. Okay, so if we have a look and actually go into the formula that we're using in Excel, okay, we start with our B12 cell. Okay, we click on that, and what we can do to inspect this formula, we can click up here in the formula bar. Or we can see that Excel is plotting, or Excel is calculating rather, the y values, or getting the y values from this blue square, and getting the x values from this green square. So far so good. But let's have a look at what's happened in E12. Okay, so we click on E12, click up here. What it's done is Excel, as you've clicked and dragged it over, Excel has updated its references, okay, to these cells, and because you've dragged this cell across, okay, it's dragged across the green box and the blue box over to here now. And obviously this isn't good because we want the blue box here, but we want the green box all the way back here in the time column. So in order to get Excel to actually keep the green box static, okay, we can use this thing called absolute referencing. So let's delete these incorrect formulas, and we can go back to our correct one here. What absolute referencing is it tells Excel when I click and drag, do not change particular references. Okay, so you can see the A4 to A9 reference, we want Excel to keep static. In order to get Excel to keep the static, what we can do is we can put $ in front of the letter as well as a number. Okay, so it goes from A4 colon A9 to $A, $4 colon $A, $9. And if we hit enter now, what we can do is when we click and drag, what we can see if we go back into E12 is that Excel has fixed in place the green box, and it's actually updated the blue box as we've dragged. And so this thing is called absolute referencing. It's quite useful to know. What we can also do is get Excel to work out this thing called the R² value. Okay, so let's get in the next row, get Excel to work out the R² value of our line. Now, what we want to do is we want to get Excel to work out the R² value, which is, I guess, a goodness of fit indicator. So the R² value will essentially say to us, okay, if we come back here and draw the linear line again, okay, what we've done up here in the slope, okay, is we've got an Excel to work out for us exactly the gradient of that line there, okay, and in the next cell over here, Excel has worked out for us the gradient, or the slope, of this line there. What we want Excel to do now for us is to tell us how good the data fits these particular lines. And the R squared is a measure of this goodness of fit. Okay, so just like we did the slope function before, what we can do is we can use the R squared function this time. So again, to insert a formula or a function into Excel, you type equals, and then followed by the name of the function. In this case, it's RSQ. Start the brackets up, and again, we want it to calculate the goodness of fit of the line, which was data points between 0.25 and 1.5 minutes for absorbance, and the X data points were the minutes 0.25 to 1.5. And again, what we can do, because we want to click and drag, we can put dollar signs in front of the letter and also the number, press enter, and we can click and drag that across. So the closer these R squared values are to 1, the better our goodness of fit. And so we can tell these data points are all 0.99 or above, and so our slope, we can have good confidence in our slope. The next step in our LDH calculation is to work out the rate of activity. Now, if I go to pen mode and draw this, okay, we know by the Beer-Lambert law that the absorbance is equal to the extinction coefficient times the concentration times the path length of the cuvette. Now, if we just chuck a few deltas in front of the A, okay, the change in absorbance, therefore, is equal to the extinction coefficient times by the change in concentration times by the path length. Okay. Over here, what we have is we have the slope, which is the change in absorbance per minute, which is this part of the equation. Okay, which means that if we know the extinction coefficient, okay, of the NADH, we can work out the delta C, the change in concentration of the NADH, since the path length of the cuvette is 1 centimeter. Okay, so let's have a think about that more deeply. If we have a look at, for example, our first data point here, okay, the slope, the delta A is 0.1726. So if we have delta A equals the extinction coefficient times delta C times the path length, therefore we have 0.17 is equal to the extinction coefficient of NADH, which is 6.2. The units are per millimolar per centimeter, and times by the delta concentration, whose units will be in millimolar, okay, per minute, times by the path length of the cuvette, which is 1 centimeter. This unit over here is actually absorbance over time, and so this has the units absorbance per minute. So what we can see is that in order to get the delta C, and the units are millimolar per minute, it's just going to be a matter of the absorbance over 6.2. Okay, and let's get my calculator out. 7 divided by 6.2. That's going to be equal to 0.027 millimolar per minute. Okay, so 0.027 millimolar per minute is the rate of change of our concentration. So just to recap, our calculation of the delta concentration, or the change in concentration over time, came about like this. We had delta A equals the extinction coefficient times by the delta concentration times by the path length, which means that the change in concentration is equal to the change in absorbance divided by the extinction coefficient times by the path length. But the path length is 1 centimeter for us here. Okay, so this means that if we want to put our change in concentration down here, and this unit will be in millimolar per minute, okay, it will essentially be delta C equals delta A on EL, sorry, which means that it will be this, okay, which is the delta A, divided by this, which is the extinction coefficient. Okay, so let's put that down in Excel right now. We can call this the rate of change, okay, and the units, as we said before, can be millimolar per minute. And this is equal to, again, just the slope, okay, which is the delta A divided by the extinction coefficient. So notice how, again, we've just entered a formula into Excel. Okay, we're using Excel to calculate things for us. And so we've done equals the absorbance B12 divided by the extinction coefficient, which is in J12. And now what we can do, again, is we can drag over. But before we drag over, we need to fix J2 such that J2 does not move. Okay, so in order to do that, we put a $ in front of the J, $ in front of the 2. We press enter. That's absolute referencing. And then we can click and drag, and it will make J2 stay, but it will move the blue cell around. So before we proceed, I'll just show you one other way of referring to a particular cell in Excel, and this way you don't have to use absolute referencing. Okay, so let's just delete these that we've made so far. So coming back here, we've divided the slope B12 by the extinction coefficient J2. What we've done is we've referred to J2 using absolute referencing. But what we can do instead is you can see how if we click into J2, the extinction coefficient value, up here in the top left, we have something called the name box. What we can do is actually we can give this particular cell a particular name. And you can use any name you want within reason. Excel has reserved some names, so you can't use particular names. Like you can't use the name slope, for example, because that's a name of a function in Excel. But what we can use is any English word, and so we can call it the extinction coefficient, no spaces, or just to kind of show you that you can use any name here possible. Let's just call this name dinosaur. Okay. And we just type in dinosaur, and make sure you have to hit enter after you type in the name. Okay. And now wherever we want to refer to 6.2, the extinction coefficient, we just have to type in dinosaur. Okay, so if we come back here to our calculation for the rates, instead of saying $J$2 here, we can actually type dinosaur. Okay, and you can see how Excel has now recognized that this dinosaur word is referring to J2. It's labeled this green, and it's highlighted J2 green as well. And so if we click enter and drag that across, that's another simple way of referring to a cell in Excel. Okay, so let's just pause and think about what the calculation we just did actually means. So the rate that we just calculated is the delta C, and the units are in millimolar per minute. So if we take this one for example, okay, the delta concentration in the patient's serum, okay, when there's 5 microliters of the patient's serum being used, the change in concentration of NADH was 0.027 millimolar in every minute. If we expand this out, what this will look like is 0.027 millimoles per liter, okay, per minute. And let's take that down, 0.027 micromoles per milliliter per minute. Okay, let's take that down once more. We can express this 0.027 micromoles per mil per minute. We can just change this left side here, the 0.027 micromoles to nanomoles. So 0.027 micromoles is 27 nanomoles, and the rest of it doesn't change. So what this means to us is that every minute of the reaction, okay, in every mil of the reaction, there are 27 nanomoles of NADH being produced. Okay, so it means that in the cuvette, okay, in your cuvette, in every minute, in this 1 mil, okay, there are 27 nanomoles appearing. And you can see how 27 nanomoles is a much nicer number to deal with than 0.027. So what we can do in Excel is we can actually multiply this value here, okay, we just have to times that by 1000, and we can change these units to nanomoles per mil per minute, and it'll make life a bit easier for us. What we can also do is, because this mil is essentially the volume in a cuvette, let's change this to nanomoles per minute in the cuvette. Okay, so let's do that calculation. Remember what we're doing is we're just we're timesing this out by 1000 to give us a nice number, which is 27. And so what we can do is we can put the existing formula in brackets, and then we can just times by 1000 and then press enter. Times in Excel, remember, is just the asterisk. And then we can drag this formula across so that it updates. And remember, we always have to update our units, and so this would be nanomoles per minute per cuvette. And again, just double click between the A and B to stretch this column out. So the next step is to calculate what we call a velocity of our serum. Okay, so the velocity of the serum is expressed in units. Okay, and for enzymes, the international unit, so 1 unit is equal to 1 micromole of substrate to product in every minute of a reaction. Okay, so you can see that we've kind of got moles here, or nanomoles here. We've got minute here. Okay, so we just have to find a way to express, I guess, this in terms of the patient's serum volume. So let's go through that calculation. Okay, so what we have from this particular row, okay, is that we have just taking again this 27 nanomole per minute per cuvette example. Okay, so the rate of reaction is 27 nanomoles per minute per cuvette. Now, this reaction, okay, this appearance of 27 nanomoles in every minute of the NADH in this particular cuvette arose because of the action of the 5 microliters of the patient's serum. Okay, which means that we can also say 27 nanomoles per minute, okay, arose because we had 5 microliters of serum inside this cuvette. Now, what we can do is we can divide this by 5 to bring it down to 1 microliter of serum, and therefore we divide this by 5 as well. So 27 divided by 5 is about 5.4. This would be nanomoles per minute per microliter serum. And let's just convert this nano and this micro up by 1000. Okay, so this would be 5.4 micromoles per minute per mil of serum. And what you can see here is that we've got an expression that is micromoles per minute. And remember, micromoles per minute is equivalent to a big U. So what this means is that we can write 5.4 big U per mil of serum. Okay, and this is the velocity of our serum. And so what we can do is we do this calculation in Excel, and remember what we've done here is we've just taken, quite simply, we've taken the number 27, okay, and we've divided it by the number 5. So what we can do in Excel, we can do that. We can do 27 divided by 5, and we can put that value down here. Okay, so let's call that the velocity, and remember the units were going to be in big U per mil of serum. So that was equal to the rate simply divided by this number, number 5. So remember how I said at the beginning how we put numbers into Excel, and we don't just put our 5 ULs here, for example, because otherwise Excel can't use that number 5. But if we put the number 5 by itself, Excel can actually go in and use this number for our calculations. Okay, so B14 divided by B3, press enter, and this time we can drag across without using any absolute referencing because we want it to update, okay, both the green and also the blue. So what we see here is that we've got a bunch of velocity recordings for different replicates for our patient's serum. And so this velocity reading came about when we used 5 microliters of the patient's serum. This one came about when we used 10 microliters, and this one when we used 20. These values have been corrected, in a way, already for the amount of serum that you added. If you notice back in this particular row here, okay, you notice that the rate of production, okay, the number of nanomoles that were appearing, okay, of NADH per minute in the cuvette were, in a way, corresponding to the amount of enzyme that was added, okay, or the amount of serum that was added. And so you see here that when 5 microliters were added of the serum, okay, the rate of production of NADH in the cuvette was about 27. You expect that if you add twice the amount of serum, then the rate of production would double, and that's kind of what you see here. And again, if you go from 10, double it to 20 microliters of serum, that should technically double the amount of LDH enzyme going into the reaction, and therefore the rate should be about twice that as well. So 47 to 83 is about double, so we're in the ballpark. And so again, just this last row here has corrected for, or accounted for, the amount of serum that we've added. And all we need to do now is we just need to find the average. Okay, the average velocity, that's units per mil of serum. And let's just put that guide down here, and so what we'll do is we'll select these 3 cells, do a merge in center, and then we'll do equals the average, okay, using another Excel function called average. And here what you do is you just feed Excel a set of numbers, and the easiest way to do that is to click and drag along the numbers that you want. Okay, so equals average, start the parentheses, then we click, and then we drag, release the mouse, close the parentheses, and press enter. You can do the same here. So merge and center, type equals average, start the brackets up, select what you want, close the brackets, and press enter. And after we find the average velocity from our patient serum, okay, versus our normal serum, we want to compare how much greater the velocity is in our patient serum compared to our normal person serum. So let's over here find out the fold change. And the fold change is just very simply how many times higher is this compared to this. And to do that, again, we use Excel. We say equals this divided by this. That will give us 39.7, for example, which means that the patient activity, okay, the activity of LDH in the patient serum is about 39.7 times higher than the activity of LDH in the normal patient's or normal person's serum. So just one last little formatting issue here. What we can do, not absolutely necessary, but what we can do is you notice that there are a lot of decimal places, a lot of significant figures around in these calculations. So what we can do in Excel very simply is to use these buttons here, okay, increase decimal and also decrease decimal, to change the number of decimal places that actually show. So if we click decrease decimal, what you'll see is that over time as we click it, okay, it will very easily allow us to reduce the number of decimal places shown, just to make our numbers look a bit neater. Okay, so just to recap, what we've done is we've taken, we started out with these values here, which were, or actually these values here, which were the replicate values for our absorbance readings, okay, at different volumes of patients and also different volumes of normal serum measured over time. Remember, the time was expressed in minutes because everything else here is in minutes, okay, so it's good to keep your units consistent in Excel to make the calculations easy for you. I showed you how to type a micro in Excel, or anywhere really, by using an Alt code. So you press Alt on your keyboard, and then at the same time you type 0181 using the numerical keypad. I showed you how to do the superscript for the per millimolar per centimeter, and also we went through how to name a particular cell to get Excel to refer to that cell when necessary. We went through the slope function, okay, and how the slope function accepted the y values first, followed by the x values. And we also went through absolute referencing to tell Excel to fix a particular set of cells so that it doesn't update when you click and drag. We went through also the r squared function and said that an r squared that's close to 1.0, okay, means that your particular line has a very good fit to the data points. And those data points were down here in the graphs that we drew, okay, one for patient, one for normal serum. And remember, we didn't get Excel to draw an automatic trend line. Instead, we drew this manual line using just the drawing toolbar. And this was to prove to ourselves that the rate of change of the absorbance at 340 actually started to taper off over time. Okay, and what we did after that is, after we found the slope, okay, the rate of change in the linear part, okay, the rate of change in the linear part of the curve, we went back here and calculated the rate in our cuvette, okay, the rate of change in nanomoles per minute in our cuvette, by using the extinction coefficient here, which we called dinosaur. After that, we took into consideration the volume of serum, okay, by dividing the rate by the serum volume. We found out the average of these three replicates and the average of these three replicates, and then we found out the how much higher the velocity was in the patient serum compared to the normal serum. So that's Excel for LDH for you. Thanks for listening, and I hope you've picked up some useful tips and tricks for Excel along the way.